Okay, so continuing with our design methods using root locus, what we will see in this particular lecture is design criterion to improve the steady state performance. And steady state performance essentially means reducing the steady state errors, either getting them to 0 or having them below some predefined values. This is done with something which we call a lag compensation. Lag compensation is an approximation of an integral control. We saw how adding an integrator increases the type of the system. Increasing the type of the systems helps me track signals in a better way, right? So we had this little relation between what is the relation between a type 2 system and the acceleration error constant, the velocity error constants, and so on, right? So this lecture we will focus on the lag compensation, which is an approximation of a PI controller. Okay, so let's start with an example, right? So given a plant, a certain transient specifications which translate to zeta being 0.5, omega n being 2.7. These are my transient specifications, and the steady state specification says that my kV should be greater than 10, right? Okay, so first I draw the root locus. And I see that at a certain value of gain k, which is 32.4, my root locus passes through the dominant poles. Right? The root locus passes through the poles which are defined by this zeta and omega n. Okay, so I don't really need to worry about the transient specifications because my root locus actually passes through those points by just mere adjustment of the gain. Okay, let's now worry about the steady state error. The error constant kV here is 1.8, and I want to make this larger than 10. So the question here is, can we design a compensator in such a way that it has kV greater than 10 but not really alter this? I don't want this thing to be messed up, right? I want to design a controller such a way that this steady state specification is met by not disturbing too much of what is happening here in terms of the transient specifications. Okay, let's see how we can do that, right? So consider again a standard closed loop system, right? So I have the error, a gain k, a plant g. The open loop transfer function is given by this, where g has a set of poles. G has set of zeros, a pole at the origin, and set of other poles. Right? So the transient specifications require the dominant closed loop poles to be at some ST, right, which are computed by these two numbers. Okay, the first thing is, assuming there is a k greater than 0 such that the root locus passes through SD, we compute the gain k in the following way. Again, this is just the magnitude criterion, that g times h was equal to 1, or in this case k times gs would have its magnitude to be equal to 1. Okay, then we look at the steady state error, right? Kv is limit s tends to 0 of this entire number, and I'm deliberately looking at a type 1 system, right? Because a type 0 system cannot track a ramp input, whereas for a type 2 system the steady state error is 0, kV is 0. So if kV is some finite number, I'm essentially looking at a type 1 system. Again, we can refer to this table. Okay, so how would this look like? Well, the lag compensator provides this facility. So the first thing I would, if I look at the ideal integral compensator, I would say that I should place a pole at the origin, which means, well, which would eliminate the steady state error completely. But what I told you is that an ideal integrator cannot be realized. So what you will say, well, just put it slightly to the left, this can be realized, right? That would be the first thing, right? In the lead compensator we just said, okay, just add a 0 because it pulls my root locus to the left, and we see that it has its own set of troubles. Now if I just add a pole slightly to the left, say instead of 0, let's say I add at 0.05. Okay, now does this meet the steady state conditions? Possibly, but what this will do is it will contribute certain angle, right? So this G or GC will contribute certain angle to the plant, and then this condition would be violated. That's easy to check. So we want to add this pole here in such a way that it does not contribute to the angle, or the angle contribution is as minimal as possible, and therefore I start with this pole and I add a 0 slightly to the left. I can say, why not to the right? Well, I don't really want, so I want again the dominance condition to be ensured so that the pole moves to the left. Okay, and by construction also it is kind of obvious. So the lag compensator by construction looks like this, in such a way that the beta now, which is analogous to the alpha earlier, this beta is now greater than 1, and Z and P must be placed so close to each other that the angle contribution is less than 5. I cannot make it 0, because if I make it 0, the pole would sit on the 0, they would cancel out each other and there would be no compensation, right. So it is desirable to have G, the angle of GC, to be as small as possible to have the least effect on the transient behavior. So that is what we have to be careful in this design procedure. Okay. So here in this case, this is the compensating pole, the 0 should be to the left of the pole, right, contrast to what was happening earlier, that the 0 was to the right of the pole. Okay, first let us see what is the effect of the closed loop gain k while we add the lag compensator. Earlier we had computed the gain to be something like this, right, k, this in such a way that SD was passing through the root locus. Now how much does the gain change when I add a lag compensator? So k cap, which is the total gain when I add a lag compensator, is the original gain k plus this extra factor. Okay. Now the reason why we place these two close to each other are also that the k cap should be as close to k as possible, right, and these magnitudes, if you see, they are kind of almost equal because these are very close to each other. So k cap, for k cap should to be equal to k, this ZSD plus ZG, the magnitude of this should be the same as this one, right. So this is also what is desired, in such a way that we really do not disturb the transient requirements. Okay, now what is the error constant for the compensated system? The velocity error constant is k tends to 0, k cap GC times G, right, and this turns out to be, this is kV ZG by PG, and this kV is the kV of the uncompensated system, this guy, kV of the uncompensated system. Okay. Now when I were to design this compensator, I am now worried about what is the location of these poles and zeros. Okay. And the unknown, one of the factors that was deciding was this beta. Beta is an unknown and tau is the other unknown. Okay. kV of the compensated system is related to the kV of the uncompensated system via these two numbers, Zg and Pg, and based on this construction of the compensator, Zg by Pg is beta. Okay. Now I know how to find beta, right. This is known to me, right. This is from the given specification. So I can find out what is beta. So for the appropriate design, we must have beta as the ratio of the desired error constant to the error constant of the compensated system, which helps me in finding the location of Zg and Pg appropriately. Okay, so how are these guys placed? So first thing is to obtain a large range of factors. I would have them as close to the origin as possible, say at 0.1 or 0.001 and so on. So the factors can be increased by just so if I am at 0.1 or 0.01 and I want to have a factor of 10, I can easily go to 0.1, right, and so on. So the 0 must be made as small as possible and Pg must then be fixed. So I first select the 0. Once I select the 0, since I know beta, I can fix what is my PG, right. So, what must also be ensured is that the angle contribution is as minimal as possible, right, less than 5 degrees. Unlike the lead compensator, there is no constructive way here, neither a graphical way of choosing ZC and PC, right. There we had a beautiful way of finding the gamma, which maximizes the alpha, and we could explicitly compute the formulas. So here what we will do is we'll just look at a graphical method which without much proofs of what is happening, but what this method will ensure is that the angle contribution is less than 5 degrees. Okay, so what do? Is I take this constant zeta line, or the line joining the origin to SD. From this line I draw another line which is at an angle less than 10 degrees, should be 7 or 8, really you could do a little modification once we have the first iteration of design. So once I have this, say I fix this angle at 9 degrees, I just draw another line, and this will give me the location of the 0. Once I know the location of 0, I can easily find what is the location of the pole, right, with this formula, because I know beta, and beta is derived by comparing the desired error constant to the error constant of the uncompensated system. Okay, so again back to the example. Right, so we knew that just by adjusting a gain to 32.4, the transient specifications are met. Now I am interested in the steady state specification. Right, the kV of the open loop or the uncompensated system is 1.8, and this is not satisfied. It's quite obvious. Okay, now this is the desired error constant. So beta is kV hat by kV is 5.4, and beta is always greater than 1, right. So now just by doing the method as suggested earlier, if I put my 0 at 0.1, the pole location turns out to be at 0.108, and the lag form of the lag compensator is something like this. I will not really have a gain k here because I don't really want to do, so the gain contribution of this entire thing should be as close to 1 as possible, right. And what is the angle contribution? Well, it's just 0.89 degrees, it's less than 5. So the lag compensator does not really alter the transient performance too much, as we see here, right. So the uncompensated system, the red one, which was the root locus of the uncompensated system with just the gain adjustment, is the red line, and we see the blue line is just slightly to the right. Now this is not very surprising, because I am adding a 0, adding a pole at the origin, and this has the effect, or pole very close to the origin, this has the effect of pulling the root locus slightly to the right. But what we saw here is we are improving the steady state performance by having just very little effect on the transients, and we could maybe alter this slightly to 0.09 and check such that the effect is minimal. It will never be a condition that the red and the blue lines match completely. So what we would see from this plot is that the original gain of 32.4 would not work, because it does not really lie on the root locus. The root locus has moved slightly to the left. So what is the new gain k that we would choose? One method is to fix up the constant zeta line, right, and then see the intersection of the constant zeta line with the new root locus, which is slightly shifted to the right, and then compute the new gain, right, and that would turn out to be 32.65, right. So that is what we would do here, right. And if so, a constant zeta line would ensure that the peak overshoot does not change at all. But if we are more interested in the settling time, then I would look at the intersection with the constant omega n line and then choose the gain appropriately. It depends on what kind of specifications I am looking at. So this slight gain adjustment is just done by the root locus here, by looking either at the constant zeta lines when my transient when my peak overshoot is more important, or the constant omega n line when my steady state or the settling time is more important, right. So, this is just like the basic design procedure for a lag compensator. So, we have seen how lag compensators helps in improve the steady state response in terms of the steady state error. In the next lecture, we will see, given a certain system where neither the transient specifications are met nor the steady state performance requirements are met, in that case how we will compensate the system, where we would need combination of both the lead and the lag compensator, and we will see how to go about the design procedure in that case. Thank you.